So first of all, the graphs in simple harmonic motion discussed are displacement time graph, velocity time graph, acceleration time graph, acceleration displacement graph. So first of all, let me tell you that I have taken the example of a wooden block tied with a spring. The block is pushed to point B, that is the leftmost extreme, and its amplitude is minus x naught. When this is done, the spring is compressed, and when it is compressed, elastic potential energy is stored in the spring. And when the spring will be released, its elastic potential energy will be changing into kinetic energy in such a manner that the block will accelerate towards O. And when it passes O, at the point of O, its velocity will be maximum and kinetic energy will be maximum. Whole of the elastic potential energy will have been given by the spring to the block. The block keeps on moving to the right until it reaches A, which is a distance x naught on the right of the mean position O. At A, the block again stops and returns and keeps on moving between B and A, time and again crossing O, which means that it is performing simple harmonic motion. If we talk about time, I have taken time equal to 0 at original position when the block is going towards A, and its velocity is V maximum, shown by green arrow below the block diagram. And when it crosses position O leftward, its velocity will be minus V, and it will again be equal to the maximum velocity. At time t equal to t over 4 seconds, the block will be at A because it will have completed 1/4 of the simple harmonic motion. Then at t equal to t by 2 seconds, it will be crossing O leftwards. And at t equal to 3t by 4, it will be at B. This way it is going to continue moving, and we are assuming that there are no energy losses, as we have assumed that the block and the surface are smooth surfaces. I have made a displacement time graph in black color. At time t equal to 0, as the block was at O, its displacement was 0. And at A, its displacement was maximum equal to x naught. And at O again, when it came back to O, its displacement was again 0. And when it crossed O towards B, the displacement became negative, so the displacement time graph will come to the negative half of the graph, that is below the time axis. And since the graph is continuously accelerating and decelerating, it will be a curved graph as shown in the black graph. At O, when the velocity is maximum while it is going towards A, the gradient of the graph will be maximum positive, whereas at O, when it is going towards B, its velocity will be maximum, but the gradient of the graph will be negative because the velocity is negative maximum. Having discussed the displacement time graph in detail, now we can sketch the graph of velocity as well. So as you can see that on the displacement time graph, I have drawn the velocity time graph as well, which is in green color. And you can easily understand because we already know that velocity time graph is according to the gradient of the displacement time graph. The restoring force, because the force is directly proportional to the acceleration, so restoring force in the spring is going to increase as the displacement increases. I have shown a diagram in which the spring is in its original size, so no force is applied, hence no restoring force is there. However, when the spring is compressed to B, the restoring force in the spring will be acting towards right because displacement of the block is towards the left of the mean position, and the acceleration will be maximum when the restoring force is maximum, and acceleration will be zero when the restoring force is zero. That means at B and at A, the acceleration will be maximum, and at O, that is the mean position, acceleration will be zero. Now, if we have to write an equation or relation between A and X, it will be A proportional to negative of the X, and A will be equal to minus omega square X. Omega is the circular velocity or the angular velocity. The acceleration curve will lie on the opposite side of time axis as compared to displacement curve. And if you look at the graph, the black one is a displacement curve and red one is a acceleration curve. And can you see that the acceleration will be maximum when displacement is maximum, that is points B, and at the mean position the acceleration is zero. The negative sign tells that the acceleration displacement graph will have a negative gradient, and A will be maximum when displacement is maximum. I have drawn the graph for you. So A will be taken as plus minus omega square x naught, the definition of simple harmonic motion. I have written the definition as a body is said to be in simple harmonic motion if its acceleration is directly proportional to its displacement x from mean position, and acceleration is always directed towards mean position. Whenever the definition of simple harmonic motion will be asked in the question paper, it will have 2 marks at least. And if you look at the definition, there is a underline in blue and there is an underline in black. These 2 points you have to write down to score the full marks for definition of simple harmonic motion. Here I finish the graph section and the definition. Here I would also like to request my viewers that it helps to increase my morale and my efficiency when somebody likes my videos, my lectures, and also gives me a thumbs up and maybe also subscribes